According to Greek mythology, the sun god Helios drove the chariot of the sun west across the sky each day, and then back east across the ocean each night. One day his son, Phaeton, came to him asking if he could drive the chariot. Reluctantly, Helios handed over the reins. But when Phaeton took charge of the chariot, he lost control, and the sun parched the earth. In punishment, Zeus struck Phaeton with a thunderbolt. Phaeton fell to the earth dead in a ball of flames. The Greek philosopher Eudoxus once declared, "I would willingly burn like Phaeton, were this the price for reaching the sun and learning its shape, size, and substance." And that, I think, is the attitude of the scientist. Some people just live their lives from day to day with no intellectual curiosity. Others, from time to time, when they're alone and their lives are quiet, wonder at the universe and its workings. But then there are others who have a burning desire to understand. They're driven by their need to comprehend the world, and their ignorance agitates them. They don't accept nice, overly simplistic answers just so that they can say they know the answer for appearances and status. They want to actually understand the world. These are the ones who become scientists, and Eudoxus was one. Today we know the sun's size and shape and substance. We know how and why it burns, and we get it for free. Eudoxus never did learn the answers to all of his questions. A scientist never does. But in his searching, he developed the first geometric model of planetary motion, among other things. But his accomplishments weren't made in isolation. They rarely are. To tell his story, we must first tell the story of Plato in his academy, the first institution of higher learning. Plato was born sometime around 428 BC, in the midst of the Peloponnesian War. He was born into privilege, the son of well-connected parents. As a young man in his 20s, Plato served briefly in the war near its end, as the forces of democracy and oligarchy were fighting for control of Athens. The 30 tyrants who took over around this time included 2 of his own relatives. But most importantly for history's sake is that Plato was one of those Athenian youths following and imitating Socrates, and supposedly being corrupted by him. In fact, Plato was Socrates' best student, or at least that's what Plato tells us. You see, most of what we know about Socrates comes from Plato. So in 399 BC, when the Athenian state executed Socrates, Plato was no doubt deeply affected. Given Plato's background and connections, he may well have aspired to public office at one point in his life. But with his friend and teacher's execution, and his relatives' involvement with the 30 tyrants, he was less eager for that life. Instead, he turned to philosophy and study. He spent the next several years traveling and writing. Do you remember Philolaus the Pythagorean? He was the one who had fled to Tarentum when the Pythagoreans were being persecuted and massacred, then came up with the theory that the Earth and an anti-Earth both revolve around a central fire every 24 hours. Well, according to tradition, he wrote, but did not publish, a comprehensive work on Pythagorean doctrine, and Plato paid a very high price to obtain it, then copied it, making it public. The work, of course, is lost today. Philolaus's most famous student was the mathematician Heraclitus, and Plato set out to pay the man a visit. So he set sail for Tarentum in southern Italy, where Heraclitus lived and taught, to learn mathematics and to understand the old Pythagorean institutions. Along the way, he stopped in Syracuse and Egypt, as had so many Greek philosophers and mathematicians before him. By now, Plato was about 40, and it was time to settle down. He decided that his true calling was as a teacher, like his old friend Socrates. But he would have none of this informal stuff. He wanted a dedicated meeting place. To house the school, he bought a piece of land that had originally belonged to the Greek hero Academos, so Plato's school has become known as Academia, or simply the Academy, and to this day, we still refer to institutions of higher learning as academia. So what was taught at the academy? Plato wasn't interested in teaching reading, writing, and arithmetic. He certainly wasn't interested in teaching a mere business or a vocation. He wanted to enlighten students, to impart the love of knowledge and of wisdom, to turn them into philosophers and statesmen. This was probably the first institution of higher learning. The academy lasted for generations, though it obviously changed with the times. But I'm getting ahead of myself. The story of its destruction will have to wait for another episode. Plato might have had his disagreements with the Pythagoreans, but he was still quite influenced by them and their mysticism, superstition, and numerology. Although he loved mathematics, going so far as to post a sign above the entry to his academy that read, "No one unversed in mathematics may enter." Most of his fame rests on the dialogues he wrote, which tend to focus on questions of morality, not physics. What he did write on science, namely the Timaeus, would be considered silly by modern scientists. Not just because it's wrong or because it deals with numerology and astrology, which of course it is and it does, but because it appears utterly impervious to experimental science. He seemed to believe you could just think your way through the workings of the universe. No reason to actually observe it that closely. In fact, observation might lead you astray. Let me explain why. Plato taught that the things we see with our eyes are an illusion. Every object that you see is actually an imperfect representation of the true, ideal form. There's an ideal rose, an ideal dog, the ideal planet. It's sort of like the shadows cast on the wall of a cave. You might only be able to see the shadows, but the shadow isn't the true thing. It's just a shadow of the true thing. The ideal form is the only truth out there. There's no use in studying the roses or the dogs or the planets that you see, because they're merely shadows of reality. Plato's Pythagorean side also led to a peculiar belief that endured for quite some time: the importance of the Platonic solids and their relationship to the four elements. Make a two-dimensional shape whose sides are all the same length, like a square. We call that a regular polygon. Now try to make a three-dimensional shape out of regular polygons with the same number of faces meeting at each vertex, like a cube. We call that a regular solid, or a Platonic solid. And the Pythagoreans were obsessed with them. It turns out that there are only 5 that you can construct. You can prove it mathematically. There are only 5. This must have seemed mysterious. To the Pythagoreans, steeped in mysticism and numerology, there must be some sort of cosmic significance in this fact. And according to some sources, they tried to keep knowledge of one of them secret from the public. The dodecahedron. You might remember Hippasus of Metapontum from episode 2 when I talked about the Pythagoreans. Back then I told you of his untimely death after he disclosed the existence of irrational numbers. But according to other sources, he met his fate after divulging to the uninitiated how to construct a dodecahedron inside a sphere. So of course, Plato wasn't the first to discover these regular solids. But he associated them with the 4 elements: fire, earth, air, and water. Oh, did I say 4 elements? He also included the 5th mysterious element, known as quintessence, or ether. While the 4 normal Greek elements made up matter on Earth, the ether was what was supposed to make up matter in the heavens, and it was represented by the most mysterious and secret of the 5 solids, the dodecahedron. 5 elements, 5 regular solids. Now, if you'll recall, the Pythagoreans also thought that uniform circular motion was the most perfect of all motion. Although the planets appear to wander erratically through the heavens, if you could somehow analyze the motions properly, you'd find that it was really all just circles. These mystical Pythagorean beliefs were highly influential for centuries. Nearly 2,000 years later, it was Copernicus's belief that the planets must move in perfect circles that motivated him to come up with his theory that the Sun, not the Earth, was the center of the universe. And it was Kepler's thinking about the Platonic solids that led him eventually down the path to his famous laws of planetary motion. In any event, one day Plato challenged his students. Can't anyone once and for all show how all these complicated motions that the planets appear to have are really somehow just perfect uniform circles? And that challenge was met by one of his old students, Eudoxus of Cnidus. Eudoxus was born in Cnidus, in the southwest of modern-day Turkey. As a young man, he studied mathematics under the same Heraclitus that Plato had visited during his travels. And at the age of 23, he traveled to Athens to study at Plato's academy. Eudoxus had a very different background from Plato. Where Plato was born into a distinguished family, Eudoxus was poor. His travels had been paid for by a friend, and when he got to Athens, he couldn't afford to live there, so he stayed in Piraeus, about 10 kilometers away, and walked to Athens every day. He didn't stay long, however. Possibly he was dissatisfied with the lack of Greek astronomical observations. The best observations came from Egypt and the Babylonians. Whatever the reason, he decided to leave after just 2 months and made his way to Egypt to study astronomy with the priests there. There he studied and made his own measurements of the sky at an observatory near Heliopolis. He remained in Egypt for 16 months. He then went to Cyzicus, in the northwest of modern-day Turkey, earning his living as a teacher, before returning to his homeland of Cnidus, where he built his own observatory for astronomical research. Now, we're mainly interested in Eudoxus because of his contributions to astronomy, but I should mention that much of his fame rests on his mathematical insights. He developed a method of calculating the area inside of a shape, called the method of exhaustion, that's sort of bordering on calculus. Some say that the world's most famous book on mathematics, Euclid's Elements, was based on his work. But I'm supposed to be talking about physics right now, not mathematics, so I'll leave it at that. So when Eudoxus returned to Plato's academy in Athens, he came not as a student, but as a master with his own students. And when Plato challenged his students and colleagues to analyze the motions of the planets, Eudoxus was just the person to do it. As we've seen before, the planets have a strange motion in the sky. From time to time, they make a loop in the sky, which we call retrograde motion. You've seen this picture before, but notice what I've done to show you this. Night after night, I show you the stars in the same fixed position. But of course, the stars themselves appear to rotate around the Earth over the course of a night, and this complicates things. But you see, of all of the lights in the night sky, the stars have the simplest motion. They rotate around about once every 23 hours, 56 minutes, and 4 seconds. You heard me right. You might have thought the stars rotate around every 24 hours, but no, you're thinking of the sun. For the stars, it's actually every 23 hours, 56 minutes, and 4 seconds. We call that a sidereal day. All the other lights in the night sky, the sun, moon, and planets, do something more complicated. But the stars? They just move around in a circle day after day, month after month, unchanging. At least on the timescale of a human. And because of that simple motion, it's convenient to treat them as fixed, like the wallpaper of the sky, the canvas on which the motion of all the other lights are painted. So when we want to analyze the complicated motions of things in the night sky, we'll draw them relative to the fixed stars. But in the end, if you want to know the full motion of any of the objects in the sky, you have to remember to add back in the rotation of the stars. This is what I've done with the motion of Mars here. I'm showing you how Mars moves relative to the stars by showing snapshots of the night sky that are 23 hours and 56 minutes apart. Or in other words, one snapshot every sidereal day. So how does the sun move relative to the fixed stars? It's a little slower than the stars. It takes a full 24 hours to go around. Here, let's use the power of technology to remove the blue daylight so you can see the sun and stars at the same time. If you look at snapshots of the sky once every sidereal day, you see that the sun moves backward a little each day. And finally, after a year, it returns to where it began. Of course, no one at the time knew why this would be. They could only describe it, as I'm describing it to you. So now, let's zoom out from the Earth. And let's draw a little sphere around the Earth. That represents the sky and what we can see. It's called the celestial sphere. We can paint the stars on the celestial sphere like so. And as the Earth rotates around on its axis, the stars appear to rotate around us. Whoops! Did I just say that? The Greeks at this time, of course, thought that the Earth was standing still, and the stars were rotating around it. Once every 23 hours and 56 minutes, remember? Now let's look at the Sun. The Sun takes 24 hours to rotate around us, so it lags the stars slightly. So after one sidereal day, the stars have returned to where they started, but the Sun is a little behind. In fact, relative to the stars, it moves slowly west to east over the course of a year. Here, let's keep the stars fixed in place and watch the Sun. The path the Sun takes relative to the fixed stars over the course of a year is called the ecliptic, but don't worry, you don't have to remember that. If you remember, way back in episode 1, we saw how the Sun moves through the sky over the course of a year. That was from a single point on the Earth, which we assumed was flat. But by now the Greeks believed that the Earth was round, though we haven't seen why just yet. So now we're in a position to watch the Sun's motion through the sky over the course of a year from a point of view far from the spherical Earth. You can see how confusing it is to try to visualize both the daily rotation of the stars and the annual motion of the Sun all at once. So from now on, we'll usually just treat the stars as fixed in place, and draw the motions of the Sun and planets relative to the stars. Now let's see how the planets move relative to the fixed stars. Here Mars starts out his journey and loops around every once in a while, just as we've been seeing. Here, maybe it's a little clearer if we watch Saturn. Again, you can see this zigzagging and looping motion repeating again and again. You might notice that they both tend to stick close to the ecliptic, the line that the Sun follows across the stars over the course of a year. In fact, all the planets do this, following the path of the Sun, looping and spinning like a 5-person tango. And this is the motion Eudoxus wanted to explain in terms of perfect, uniform circles. And here's how he did it. He imagined all the planets sitting on concentric spheres. Now with all the spheres we're about to use, it can get confusing, so instead I'll put the planets on little rings, like this. It all works out the same in the end, but it's a little easier to see what's going on. First we start with one sphere. If we were to put a planet on it and spin the sphere, the planet would go around and around in a circle. That's not what we want. So instead, let's take the first sphere and attach it to a second sphere, with the axis aligned with the first. And let's rotate the outer sphere and the inner sphere at the same speed, but opposite directions. What happens to the planet? Well, nothing. One sphere rotates one way, the other rotates the other way, and the two motions cancel. So far, we don't seem to have made much progress. A complicated mechanism that doesn't move the planet at all. But here's where Eudoxus had his insight. What if we attach the axis of the second sphere, not exactly to the pole of the first, but rather offset a little? Then when we spin both spheres as before, the planet no longer remains in place. It wobbles back and forth, up and down, in the shape of what I'd call a figure 8. Eudoxus had never seen a modern numeral 8 before, though, so he called it a hippopede, which means horse fetter. Then again, I've never seen a horse fetter, so I guess we're even. Now take your whole contraption so far and put it inside a third sphere. Now, finally, when you rotate this outer sphere, the planet traces a path around the Earth, but not in a simple circle. It moves along for a little while, then loops back, and then continues. This looks very similar to the path a planet appears to take around the Earth. And it does it by moving along 3 spheres. Actually, 4. The first 3 describe the planet's motion relative to the stars, but as we know, the stars themselves appear to rotate around the Earth once every 23 hours and 56 minutes. So we need to put this whole contraption inside a 4th sphere that rotates with the stars once every sidereal day. By using this model, Eudoxus was able to describe the motions of all the heavenly lights with a total of 27 spheres. He used 4 for each of the 5 planets, plus 3 for the Sun, 3 for the Moon, and 1 final sphere for all the stars. Now, Eudoxus' model was most likely not designed to give quantitatively exact results. The idea of exact quantitative prediction wasn't really a part of Greek science just yet. They tried for only rough qualitative agreement between theory and observations. We don't have Eudoxus' writings, only the description of his theory by others. But assuming he chose the best quantitative values for his parameters that he could, it would correspond in a rough qualitative way to astronomical observations, but it was not quantitatively correct. Having said that, it wasn't long before there were objections to his theory. Eudoxus has each planet repeating the same loop exactly forever. But each time a planet loops in the sky, the loop is actually a little bit different. critics also pointed out that the planets get brighter and dimmer from time to time, which was interpreted as the planets getting closer and farther from the Earth. And perhaps more convincing, it was pointed out that eclipses of the sun are sometimes total, when the moon covers all of the sun, and sometimes annular, when a ring of the sun pokes out behind the moon. That certainly starts to look like the heavenly bodies do in fact get closer and farther from the Earth. So right from the start, many experts thought Eudoxus' model couldn't be the whole story. It couldn't be the truth exactly. But on the other hand, it was the first model to at least come close to simply explaining the motions of the planets. Oops, did I say explain? I should have said describe. His model described the motions, but it didn't explain them. No one had any idea why they moved this way, but at least they now had a geometric model of how they moved. Now, you might be thinking that it seems a bit overly complicated to have the stars in each of the planets sitting on separate spheres that each turn with exactly the same period of 23 hours and 56 minutes. I mean, isn't that kind of a strange coincidence? Well, one of Eudoxus' colleagues at the Academy, named Heracleides Ponticus, apparently agreed. Heracleides had a reputation for tall tales and pretentiousness, so much so that the Athenians nicknamed him Heracleides Pompikos. In any event, he proposed that the Earth sat at the center of the universe and rotated once a day. It would explain why all the heavenly bodies seem to have a tendency to rotate around the Earth roughly once a day. This idea, that the Earth spins on an axis, which is of course correct, will keep popping up from time to time over the centuries, only to be rejected time and again as improbable. It seemed fairly obvious that objects have a tendency to remain at rest, and that if the Earth were moving, we'd notice it somehow. So for now, at least, this idea would remain sitting unused and unloved in a dark corner of natural philosophy. Heracleides was also well respected at Plato's Academy. In fact, he might have been put in charge there while Plato was away. You see, earlier in his life, while Plato was visiting Syracuse, he met a man named Dion, who became his friend and admirer. Now, all these years later, Dion came to Plato. It seems Dion's nephew, Dionysius the Younger, was about to inherit the throne of Syracuse. And knowing Plato's devotion to teaching virtue and the formation of noble character in future leaders, and his interest in building better government, Dion asked Plato to come to Syracuse to tutor his nephew. Plato accepted, possibly leaving his academy in the charge of Heracleides. But Plato's trip to Syracuse was a debacle. Dionysius, it turns out, was no philosopher king. He quickly became paranoid that his uncle was conspiring against him. Dion was exiled, and Plato himself only escaped with great difficulty. And so Plato returned to Athens, and was back to lecturing at the Academy. And it's now that he made the most important scientific discovery of his life. Plato's most important scientific discovery was his young new student, Aristotle.